Let's elucidate the quantum Fourier transform. In this video, we will explore 5 diagrams which illustrate an interesting pattern. In all of these diagrams, time flows from top to bottom, and vertical black lines represent qubits. At the top of these diagrams, each of the qubits are labeled, and directly below the labels, the initial states of the qubits are shown. Let's begin by examining the diagram in the bottom left. This diagram depicts the single qubit quantum Fourier transform. At the top, we can see a label for the qubit, x sub 0. And below the label, you can see the initial state. The initial state is denoted by ket phi sub minus 1. Phi sub minus 1 is a bit, which can be either 0 or 1. And those two options label both of the single qubit computational basis states. So we're initializing this qubit in one of the single qubit computational basis states. So that's either the state 0 or the state 1. And then this vertical black line depicts the qubit as it goes through this procedure. So we start from the top and then we go to the bottom. And in this diagram, because it's a small diagram, we can only see one quantum gate acting on this single qubit. And that is this box with an H. That represents the Hadamard gate. So that means that this Hadamard gate is the same as the single qubit quantum Fourier transform. Now that we've seen this single qubit case, let's move on to the two qubit case. So that is shown in this next diagram, where we have two vertical black lines which represent the qubits as they traverse through this procedure. So we begin at the top, where we have two labels. We have x sub 1 and x sub 0. And beneath the labels, we can see the initial states. And those initial states are denoted by phi sub minus 1 and phi sub minus 2 inside of these kets. So those are bits. But now we have two qubits, so we can describe all 4 of the two qubit computational basis states. So they can be described as 0, 0, 0, 1, 1, 0, and 1, 1. So those are the 4 options up here. And we can initialize all 4 of those options at the top of this diagram. Then we can see the gates that are applied in this procedure. So first we have the Hadamard gate applied to x sub 1, and then we can see a controlled unitary gate. So x sub 0 is acting as the control qubit, and x sub 1 is acting as the target qubit. And here we have a 2 as the label for this unitary operator. And we will discuss these unitary operators later in this video. After this controlled unitary gate, we have another Hadamard gate, but this time it is applied to a qubit labeled by x sub 0. And then finally, we have a swap gate. So these two x signs and this horizontal line, they indicate that we are swapping the states of the two qubits. So we have Hadamard gates, controlled unitary gates, and swap gates, and they are all acting on these qubits. So these quantum gates are sufficient to implement the two qubit quantum Fourier transform. That is what this diagram shows us. Now let's move over to the 3 qubit quantum Fourier transform. So now we have x sub 2, x sub 1, and x sub 0. Those are the labels for the 3 qubits. And let's have a look at how we're going to describe the 3 qubit computational basis states. So we have phi sub minus 1, phi sub minus 2, and phi sub minus 3. These are all bits. And we can use these bits to encode a state. And that state is just going to be labeled by those 3 bits. And we have 8 options. That's 2 to the 3 options, because now we have 3 qubits. And the dimension of the Hilbert space is 2 to the power of 3. So that is 8. Let's have a look at the gates that are involved over here. So we're applying the Hadamard gate on qubit 2 over here. That's x sub 2, furthest to the left. And then we have a controlled unitary gate and another controlled unitary gate. And you can see that the label over here is 2 and then 3. So we will see what that actually means and how these gates affect the quantum state. Every time you see a black circle, that indicates that we have a control qubit. So the black circle is placed on top of the controlled qubit in these controlled gates. And the other qubit is acting as the target. So here we have the Hadamard, and then we have two controlled gates. And then after that, we have another Hadamard, but now it's acting on the qubit labeled by x sub 1. And then we have a single controlled unitary gate, and then we apply another Hadamard gate on x sub 0. And finally, we apply a swap gate. So that is the 3-qubit quantum Fourier transform as shown in this diagram. Now let's have a look at the 4-qubit quantum Fourier transform, and you might be able to see a pattern emerging over here. Inside of this 4-qubit quantum Fourier transform, you can actually see all of the gates over here. They match the layout that we have for the 3-qubit quantum Fourier transform. And inside of the 3-qubit quantum Fourier transform, you can see the gates matching the layout for the 2-qubit quantum Fourier transform. And you can keep following that pattern all the way to the beginning. You can just see this single Hadamard gate over here. That's the single Hadamard gate appearing just before the swap gate. And the swap gate is required over here because we have 2 qubits. And then when we have 3 qubits, we again require a swap gate. But now when we get to 4 qubits, we require 2 swap gates. So we're swapping the order of these qubits. So we have to swap the first with the last, the second with the second last. And that's all the qubits in this 4-qubit quantum Fourier transform. So now that we see this pattern emerging, we can jump over to the mu-qubit quantum Fourier transform. So that's in this big diagram on the right. So here we have a register of mu qubits, and mu is a positive integer larger than 4. So we've seen 1, 2, 3, 4, and then we have a look at this general case. So in this general case, we're omitting a lot of the gates and the qubits. When you see horizontal dots, they indicate that we have omitted qubits in the middle. So we're just showing the first, second, second last, and last qubits in this register. And all those dots are telling us that we have omitted the intermediate qubits. And when you see vertical dots, those vertical dots indicate that we have omitted gates. So here we have many of these controlled unitary gates that have been omitted. So we're only showing the Hadamard gate, then this first controlled unitary gate, and we're skipping over, and then we're just showing the last 2. So this one is labeled by mu minus 1, and then we have mu over here. So that mu is the same mu that indicates how many qubits we have in this register. So this describes the mu-qubit quantum Fourier transform. And you can see this same pattern. We apply the Hadamard, then a sequence of these controlled unitary gates, and then we move over to the next qubit. We apply a Hadamard, and then we have a sequence of controlled unitary gates. Here, a lot of them have been omitted. And then we keep doing this until we get over here to the second last qubit. That's denoted by x sub 1. And then we apply a Hadamard. Then we have this single controlled unitary gate. And then we apply a Hadamard to x sub 0. And at this stage, we implement all of the swap gates. So we swap the first with the last, the second with the second last, and so on. We keep swapping until we've swapped all of these qubits. Now, note that if this is an odd number, if mu is odd, then we're going to have a qubit in the middle, just like in this example with 3 qubits. So you can see a qubit in the middle that does not need to be swapped. We just need to swap this first one and this last one over here. But the one in the middle is exactly where it needs to be, so it doesn't need to be swapped. If you have an even number of qubits, then all of them are going to pair up. But if you have an odd number, the one in the middle is not going to need a swap gate. So that describes how we perform this swapping procedure at the end. And you can see some vertical dots over here, and they tell us that we have to keep swapping until we've swapped all of the qubits and we've flipped the order of these quantum states. So now that we have given an overview of the patterns in these diagrams, we're ready to introduce some useful notation. And this notation is shown in this purple box, this red box, and this blue box. So let's zoom in and have a look at this notation. In this purple box, we can see the tensor product definition of the quantum Fourier transform corresponding to all 5 of the diagrams that we just analyzed. In the first line, we can see the single qubit quantum Fourier transform. It is denoted by f sub 2 to the 1. So we're dealing with 1 qubit, and so the dimension of the Hilbert space is 2 to the power of 1, which is 2. This quantum Fourier transform is acting on a single qubit computational basis state. And we're accounting for both possible options. Phi sub minus 1 is a bit. It can be either 0 or 1. And as we saw in the diagram, this single qubit quantum Fourier transform is the same as a Hadamard gate. So if we apply a Hadamard gate to a single qubit computational basis state, then we're going to produce this superposition. One way of thinking of this is we are going from the Pauli Z eigenbasis to the Pauli X eigenbasis. So we have a superposition with a normalization coefficient of 2 to the minus 1/2. We can also write this as 1 over the square root of 2. Here we have the state 0 and the state 1 in a superposition with a relative phase factor of e to the 2 pi I times 0.phi sub minus 1. This is not decimal notation in the exponent. We're dealing with binary notation. So phi sub minus 1 is actually at the 1/2 place, or at the 2 to the minus 1 place. So that's why we have this subscript of minus 1 over here. That is telling us that we have 2 to the minus 1 multiplying this. And if we were to write this in decimal notation, that would correspond to 0.5. But because we're writing this in binary notation, we're dealing with the 0.1 place. So that 1 is actually telling us that we're dealing with 1/2. So we're accounting for both options over here. If phi sub minus 1 is equal to 0, then we have a 0 in this exponent, and we get e to the 0, which is 1. So the relative phase factor is 1, and that gives us the state 0 plus the state 1. But if phi sub minus 1 is equal to 1, then this phase factor over here, then we get a 0.1 in binary, which is the same as 0.5 in decimal, and that's the same as 1/2. And that 1/2 cancels this 2, and then we have e to the pi I. E to the pi I is minus 1. So the relative phase factor is minus 1. So we get either plus or minus as the relative phase factors over here. And that's exactly what we'd expect to see when we apply the Hadamard gate to a computational basis state of a single qubit system. Now let's move over to the 2-qubit quantum Fourier transform, which is acting on a 2-qubit computational basis state. Now we have a Hilbert space of 2 to the power of 2, which is 4. So there are 4 different options for these computational basis states. Let's see where these computational basis states get mapped to by the quantum Fourier transform. We have this tensor product definition. So when we write these brackets next to each other, we're implying that we have to take the tensor product of these superpositions. Let's have a look at the normalization coefficient. We have 2 to the minus 2 on 2. So now we have another 2 up here in this exponent. That's because each of these superpositions has a factor of 2 to the minus 1/2. And we can multiply those two factors together, and they're going to give us this normalization coefficient. If we have a look at the relative phase factors over here, we're going to see a pattern emerging. So on the right, we have the full bit string that is used to specify the computational basis states for a 2-qubit system. We have phi sub minus 1, phi sub minus 2. But on the left, we chop off the first bit in that string. And so that means this phi sub minus 2 is now at the minus 1 place. So that corresponds to 2 to the power of minus 1. That's the power of 2 that is being shown in this binary fraction. But over here on the right, we can see that all of the subscripts match their place. So this phi sub minus 1, it is at the 2 to the minus 1 place. And this phi sub minus 2, that is at the 2 to the minus 2 place. In other words, we have the 1/2 place and then the 1/4 place. Let's move on to the 3-qubit quantum Fourier transform. Now the dimension of the Hilbert space is 8. That's because we have 2 to the power of 3. So there are 8 different options for the computational basis states for a 3-qubit system. And you can see the normalization coefficient is now 2 to the minus 3 on 2. That's because we have 3 of these superpositions in a tensor product. So you can imagine implicitly there are tensor product symbols in between these brackets. Let's have a look at the relative phase factors. On the far right, we can see the full bit string that specifies the 3-qubit computational basis states. So we have phi sub minus 1, phi sub minus 2, and then phi sub minus 3. So this phi sub minus 3 term, that corresponds to the 2 to the minus 3 place, or the 1/8 place. And these other bit strings, they have been truncated. So the one in the middle, we have a missing phi sub minus 1 term. And then over here on the left, we have a missing phi sub minus 1, and we're also missing phi sub minus 2. So there is a pattern emerging over here. Now let's have a look at the 4-qubit quantum Fourier transform. So now the dimension of the Hilbert space is 16. We have 2 to the power of 4. There are 16 options for the computational basis states of a 4-qubit system. The normalization coefficient is now 2 to the minus 4 on 2. And you can see 4 of these superpositions being tensor producted together. So let's have a look at the relative phase factors. Furthest to the right, we can see the full bit string. That's phi to the minus 1, phi to the minus 2, phi to the minus 3, and then phi to the minus 4. So this phi to the minus 4 term is getting multiplied by 2 to the power of minus 4. So this is the 1 on 16 term. So we have the 1/2, the 1/4, the 1/8, and then the 1/16 term that are being shown in this bit string. So this is a representation of a binary fraction. And as we go towards the left, we can see the first bit gets cut off. We're chopping off the first one, and then we chop off the first 2, and then we chop off the first 3. And in this first qubit, furthest to the left, we can only see the last bit occurring. So these 4 examples are enough to show us this pattern. We have illustrated the pattern in this tensor product definition. Now let's have a look at the mu-qubit quantum Fourier transform. It's acting on a computational basis state for a register of mu qubits. So that's the final diagram that we saw furthest to the right. And we can see that 2 to the mu is the subscript over here for the quantum Fourier transform. And the normalization coefficient is 2 to the minus mu on 2. And now we can imagine tensor product symbols between all of these brackets. And in the middle, we have 3 dots to show that we have omitted all of those intermediate terms. If we go all the way to the right, we can see the full bit string that specifies the computational basis state that we're initializing the mu-qubit system in. We can see phi sub minus 1 all the way over to phi sub minus mu. So the second last term has a subscript of 1 minus mu. That's the same as minus the quantity mu minus 1. So if you just swap them around, then you're going to get 1 minus mu. And you can see the dots in the middle, they show all the intermediate terms. So by convention, we're only showing the first, last, second, and second last terms in this bit string. So that's the full bit string shown in this rightmost superposition. But if we go towards the left, we can see that we chop off the first bit, and then we keep chopping off bits until this term over here only has the last 2 bits, and this leftmost term only has the final bit. So that is what we're doing in this pattern. So we have the pattern, and it starts off at 1 qubit. We've seen it for 2, 3, 4, and then mu qubits, where mu is a positive integer larger than 4. So that is the pattern that we have illustrated using this tensor product definition of the quantum Fourier transform. Let's move over to the red box. The red box shows us this same action of the quantum Fourier transform. But now we're going to express it using some different notation. In the blue box at the bottom, you can see these 2 quantities, little phi and big phi. So little phi denotes the quantity that we are seeing inside of these exponentials. So we're seeing this 0 point phi sub minus 1, phi sub minus 2, all the way down to phi sub minus mu. So that bit string is occurring after 0 point. That's because we are using this notation for a binary fraction. And you can see this in summation notation over here, where we have an index going from j equals 1 up to mu. And the terms in this summation have the form phi sub minus j times 2 to the power of minus j. So in this format, we can see that the exponent up here matches the subscript. And that only happens in these definitions in the rightmost term. So the rightmost superposition has the full bit string, and all of those terms have their corresponding power of 2. But as we go towards the left, we actually see that we're nudging them, we're multiplying them by a factor, and that's nudging the entire bit string, and we're actually chopping off part of that bit string. So in this definition over here, we can also see that little phi related to big phi. So little phi is the same as capital phi times 2 to the minus mu. And if we multiply this expression over here by a factor of 2 to the mu, then we're going to get little phi times 2 to the mu is equal to big phi. So big phi is this bit string. And this bit string can also be expressed in the summation notation. And we're just shifting all of those bits. And you can see where that shift can be denoted by this multiplication by 2 to the power of mu. So we're doing mu places. We're shifting it by mu places. And now these subscripts don't actually match the power of 2 that they're being multiplied by. So that's why we have this format. We have 2 to the mu minus j. So that is just some useful notation, and we can see how capital phi and lowercase phi are linked together. So in this red box, we can see that we have capital phi. And capital phi is shorthand notation for this entire bit string of length mu. And you can see that we have a superscript mu on this ket, and that is reminding us that we're not dealing with a single qubit state, we're dealing with the quantum state of an entire register of mu qubits. And we can see the quantum Fourier transform is acting on this register of mu qubits. So that's what this notation is telling us in the red box. And then in the second line in the red box, we can see this tensor product notation, but it's in a slightly different form. So those relative phase factors are expressed using a different notation. So instead of writing this out in this full binary fraction, like we did in the purple box, we are re-expressing all of those bits in terms of capital phi. And we are multiplying that capital phi by a factor of 2 to the minus times an integer. So first we have 2 to the minus 1 in the first superposition, and then we have 2 to the minus 2. And then we keep going all the way to 2 to the 1 minus mu, and then finally 2 to the minus mu. So this is equivalent to this definition that we have at the bottom of the purple box. Why is it equivalent? Well, it's because that capital phi, it is, by definition, this bit string. And if we multiply that bit string by a factor of 2 to the power of minus an integer, then we're going to be shifting that bit string. We're going to be shifting it beyond this point. And every time we shift it, we're going to be able to cut off the integer part. And we're only interested in the fractional part. Why are we allowed to do that? Well, it's because if you have integer multiples of 2 pi in this exponential, that's going to just give you 1. So that's going to be the multiplicative identity. So we can chop off all of the integer parts. We're not interested in the integer parts, we're just interested in the fractional parts. And that is because of this periodic nature of the complex exponential. So if you were to graph these values out in the complex plane, you would see that they all lie on the unit circle in the complex plane. And if you put an integer multiple of 2 pi inside of this complex exponential, that's the same as rotating all the way around the complex plane. So you're rotating all the way around the unit circle in the complex plane. And that has no effect. It's the same as multiplying by 1. So that explains this notation over here. And explains why these are equivalent. So now that we have this format, we can write this far more condensedly using this tensor product. So we have this huge tensor product, and it's going from j equals 1 up to j equals mu. And we have this general format, and j is the value that is changing in each of these terms. So when we have this big tensor product, what we mean is we have mu terms, and all of those terms have a specific value of j. And we can just take the tensor product. And now inside these brackets, we can rewrite this in summation notation, we can introduce a new index. We can call it g sub mu minus j. And that index is going to take on values of 0 and 1. So the index is a bit. And then we can write it in this form over here. So let's examine the two cases. When g mu minus j is equal to 0, then we're going to have 0 up in the exponent. So we'll have a coefficient of plus 1. And the label for this state is also going to be 0. So that explains the term on the left. And the term on the right is explained when this index is equal to 1. So the label for the state is 1, and we also have a 1 up here in the exponential. So that's going to give us e to the 2 pi I capital Phi times 2 to the minus j. So that is equivalent. And then we can actually perform this tensor product. And what we'll see is we're going to get all of these sums emerging over here. We're going to have mu sums. And each of these sums are going to have an index specified by j. So first we're going to have g sub mu minus 1, and then we're going to have g sub mu minus 2. We're going to keep going until we get to g sub 1 and then g sub 0. And all of those indices are bits. They can take on values of either 0 or 1. And when we perform all those tensor products, we're going to have to multiply the complex exponentials. We can use exponential laws to turn that multiplication into addition within the exponent. So that explains this sum over here. And I've actually multiplied the inside of the sum by a factor of 2 to the power of mu. And that means I have to divide by 2 to the power of mu. That's the same as multiplying by 2 to the minus mu. So that explains this 2 to the minus mu and this 2 to the mu inside this up here. And then we have a sum going from j equals 1 to mu. That sum comes from multiplying all of those exponentials and then applying exponential laws. And what happens to these states? Well, we're just taking the tensor product of all mu of those states. And the labels for each of those states are the same as these indices in the sum. So we can write this in a far more compact way. Instead of thinking about all of the individual bits in this bit string, we can write this as a single value. So this can be written as the value g, and we can just have a single sum going from g equals 0 up to 2 to the mu minus 1. And we have the same normalization coefficient that has remained out the front. And what about this complex exponential? Well, we have e to the 2 pi I, g, capital Phi, and then 2 to the minus mu. So this is analogous to the discrete Fourier transform. So what have we actually done in this red box? We have shown that the tensor product form of the quantum Fourier transform is actually the same as this analogous discrete Fourier transform. So these two forms are equivalent. And this is really important because when we're applying the quantum Fourier transform, we're actually going to be using it in the phase estimation procedure. And when it shows up in phase estimation, we're going to want to use this analogous form to the discrete Fourier transform. And what we're actually going to want to do is apply the inverse quantum Fourier transform. And by convention, we can put a minus sign in the top of this exponent over here. And if we put a minus sign up there, that's going to be the inverse of this quantum Fourier transform. So that is just a convention. Some people call this definition over here the inverse quantum Fourier transform. But in these videos, I'm referring to this plus sign as the quantum Fourier transform. And if we put a minus sign in this complex exponential, I'm referring to that as the inverse quantum Fourier transform. And you can see mu over here specifies the number of qubits in the register. So now we have seen this purple box over here, which shows us 5 different examples of the tensor product format. And then in this red box, we show that the tensor product format is exactly the same as this discrete Fourier transform format. These two are just different forms of the same quantum Fourier transform. And now what we're going to do is have a look at the 2-qubit quantum Fourier transform, and we're going to examine the quantum state at key stages. This diagram depicts the 2-qubit quantum Fourier transform. We can see horizontal purple lines slicing through this diagram. These horizontal lines indicate snapshots of the quantum state at specific stages in this procedure. At the top, we can see the first snapshot, which describes the quantum state immediately after initialization. We're initializing in a 2-qubit computational basis state. Implicitly, we can imagine a tensor product symbol in between these two kets. The labels of the kets are the bits phi sub minus 1 and phi sub minus 2. These bits can take on values of 0 or 1. So that gives us 4 options for these 2-qubit computational basis states. We can have 0, 0, 0, 1, 1, 0, or 1, 1. Those are the 4 options. So we're dealing with a 4-dimensional Hilbert space because this is a 2-qubit system. So that is the first snapshot immediately after initialization. Let's have a look at the next snapshot, which shows us the quantum state after we apply a Hadamard gate to the qubit on the left. And that qubit is labeled by x sub 1. So we can call this qubit 1. So the Hadamard gate acts on this initial state of qubit 1, and it produces this superposition. We're going from the Pauli Z eigenbasis to the Pauli X eigenbasis. And we can see the bit phi sub minus 1 appearing in this exponential factor over here. That's the relative phase factor in this superposition. So this bit is the same bit that labels the initial state of qubit 1. Now let's have a look at the next snapshot. So this next snapshot shows us the quantum state after we apply a controlled unitary gate. This dark circle is placed over the control qubit, and this box with a 2, that is placed over the target qubit. So qubit 0 is acting as the control, and qubit 1 is acting as the target. Now, what is this 2 telling us? Well, this 2 is telling us that we're going to have a look at the second place in this bit string, and that's where this bit is going to appear. So now, what have we done to the quantum state? Well, we've added another bit in this binary fraction. So this first bit is, it corresponds to the 2 to the minus 1 term. And now we're dealing with the 2 to the minus 2 term. So that 2 is why we have a label of 2 inside this box over here. So we have a controlled unitary gate that is producing this quantum state. And it is important to realize that we have already got a relative phase factor over here from the Hadamard gate. So that's what this Hadamard gate has given us. And now we have added another bit to this bit string in the binary fraction that is showing up in this complex exponential. And where is this bit coming from? Well, it is the label of this initial qubit state at the top, phi sub minus 2. And specifically, it's the label associated with qubit 0. That is the control qubit. So that's where this bit string is coming from. Now, let's have a look at the next snapshot. That's what happens when we apply the Hadamard gate to qubit 0. So now we're applying the Hadamard gate on the right qubit over here, and that is producing this superposition. So now we have phi sub minus 2 occurring over here. So you can see that we're actually chopping off the bit string. So we don't have that phi sub minus 1 term anymore. We've chopped it off. But this order is incorrect. This is not the definition of the tensor product form of the quantum Fourier transform. So we have an incorrect order. How can we fix that? Well, we can apply a swap gate. So this swap gate swaps the quantum states of these two qubits. And that produces this final snapshot over here at the bottom. We have this final snapshot. So on the left, we have that bit string that consists of phi sub minus 2. So it's only a single bit in this binary fraction. And then on the right, we have this bit string that consists of both of the bits that are used to specify the computational basis state at this initial point in the procedure. So the first snapshot shows us what happens before we apply the quantum Fourier transform. It's immediately after initialization. So that's just the initial state. And then the last snapshot shows us what happens after we've applied the quantum Fourier transform. So all of these gates have had the effect of implementing the 2-qubit quantum Fourier transform, and we've applied that 2-qubit quantum Fourier transform to a 2-qubit computational basis state. And that's given us this format. Pay close attention to the normalization coefficient. In this second and third snapshot, we can see 2 to the minus 1/2. That's because we only have one superposition. We've only applied a single Hadamard gate at this point over here. And then when we apply that second Hadamard gate, that creates another superposition, and that means we have another factor of 2 to the minus 1/2. So we can bring that out, and that gives us this 2 to the minus 2 on 2. So that explains the normalization coefficient. So this is the 2-qubit case. Now let's move on to the 3-qubit case. This diagram depicts the 3-qubit quantum Fourier transform. Let's have a look at the first snapshot. This first snapshot shows us the quantum state immediately after initialization. We are initializing in a 3-qubit computational basis state. And that 3-qubit computational basis state is specified by 3 bits, which are phi sub minus 1, phi sub minus 2, and phi sub minus 3. You can see them as labels of these initial qubit states at the top. And above those initial qubit states, you can see the labels for the qubits. So qubit 2 is on the left, qubit 1 is in the middle, and qubit 0 is on the right. Let's have a look at the next snapshot. This shows the quantum state immediately after the Hadamard gate is applied to qubit 2. So we produce this superposition. We're going from the Pauli Z eigenbasis to the Pauli X eigenbasis. And note that in this relative phase factor, we have the bit phi sub minus 1. So that bit over there is coming from this initial state. So it's the label for this initial state of qubit 2. Let's have a look at the next snapshot. This is what happens after we apply a controlled unitary gate. The control qubit is qubit 1, and the target qubit is qubit 2. And we can see a 2 is showing up in this box over here, and that is telling us that we are in the second place in the bit string. So let's have a look at the quantum state. What has happened to the quantum state? The Hadamard gate has given us this phi sub minus 1 bit, and this controlled unitary gate, labeled by 2, has given this phi sub minus 2 bit. So that's what we have done by applying this controlled unitary gate. So this phi sub minus 2 is coming from the label of this initial qubit state. You can see that that label corresponds to where the control is on. So this control symbol, this black circle, is on the middle qubit. And that is where this phi sub minus 2 label is occurring for the initial qubit state at the top of the diagram. And 2 is telling us that we're dealing with the 2 to the minus 2 place in this bit string. So this is a binary fraction. The first term corresponds to 2 to the minus 1, or 1/2, and the second term is 2 to the minus 2, or 1/4. Now let's have a look at the next snapshot. So this quantum state is almost the same except for the addition of an extra bit in this bit string. Now we have phi sub minus 3. Where did that come from? Well, it came from applying this controlled unitary gate. So where is the control? The control is on qubit 0 on the right. And phi sub minus 3 is this bit that labels the initial state. So that's why we have phi sub minus 3 over here. And it is at the third place because we have 3 as the label of this unitary operator. So that is what this 3 is telling us. It is telling us that we're going to introduce this bit at the 2 to the minus 3 term. Or we can think of that as the 1/8 term. So this is the 8th term, and in the middle we have the quarter term and then the half term. So 1/2, 1/4, and then 1/8. And that is as far as we're going to go in the 3-qubit quantum Fourier transform. Now we have to take care of the middle qubit, which is qubit 1. So we're going to apply the Hadamard gate, and that's going to create this superposition. But now note that instead of having phi sub minus 1, we have phi sub minus 2 over here. That's because the Hadamard gate is being applied to qubit 1 in the middle, and phi sub minus 2 is the bit that is labeling the initial qubit state. So that's what's going on over here. Now let's have a look at the next snapshot. That's after we apply this controlled unitary gate. And what is that going to produce? Well, it's going to add this phi sub minus 3 term to the bit string. And this phi sub minus 3 term is coming from this initial state over here. That's because the control qubit is qubit 0. But why is it occurring at the second place? Well, it's because we have a 2 over here for this unitary operator. So even though we have phi sub minus 3, it is not occurring at the place where it's getting multiplied by 2 to the minus 3. It's actually occurring at the place where it's getting multiplied by 2 to the minus 2. That's because we have shifted this bit string by 1 unit. So we've moved over 1, and we have shifted the bit string by 1 unit. And that's actually gotten rid of the phi sub minus 1 term. So it does not appear in this binary fraction. We could add it in, and it would be equivalent. We could put phi sub minus 1 point phi sub minus 2, phi sub minus 3. But then that would be an integer over here. And we don't want an integer multiple of 2 pi because it's redundant. It's the same as multiplying by 1. We're only interested in the fractional part. So that's why we're writing this binary fraction over here. So that takes care of qubit 2 and qubit 1. Now we just have qubit 0 on the right to take care of. And we can take care of it by applying a single Hadamard gate. So that's all we have to do. So that final Hadamard gate in the bottom right, that is going to give us this state over here. And it's responsible for producing this phi sub minus 3 bit inside of this relative phase factor. And now we can see that this order is incorrect. We have the opposite order. So we have to swap the order around. The qubit in the middle is okay, but the first and the last qubits, they're not okay. They need to be swapped. So we can do that by implementing a swap gate. And that brings us to the final snapshot. And this over here, this is the definition of the quantum Fourier transform in tensor product form. So we have this tensor product form of the 3-qubit quantum Fourier transform. You can see first we have phi sub minus 3 by itself, and then we add in phi sub minus 2 at the front, and then we add in phi sub minus 1 and phi sub minus 2 out the front. So we're constructing that bit string. And we can also think of that as shifting. We are multiplying by a power of 2, and that shifts the entire bit string. So that is the 3-qubit quantum Fourier transform explained in this step-by-step format. Now let's move on to the 4-qubit quantum Fourier transform. This diagram depicts the 4-qubit quantum Fourier transform. In the first snapshot, we can see the quantum state immediately after initialization. We are initializing in a 4-qubit computational basis state. Let's have a look at the overview of this procedure. We can see some patterns occurring. So first we're going to apply a Hadamard gate, and that will be followed by 3 controlled unitary gates. Then we will apply another Hadamard gate followed by 2 controlled unitary gates. And then we'll have a Hadamard gate followed by a single controlled unitary gate. And finally, we will have a Hadamard gate by itself. And then we will need to implement 2 swaps. So we will have 2 swap gates to make sure that the order of the qubit states in the tensor product is correct. And we wanted to match the definition of the quantum Fourier transform. So now that we've seen that overview, and we can see these big patterns in this quantum circuit diagram, let's have a look at the labeling system. So the qubits are labeled as 3, 2, 1, and 0. The largest value is on the left, and the smallest value is on the right. So let's have a look at the second snapshot. This is after we apply that first Hadamard gate. We can see a normalization coefficient of 2 to the minus 1/2, and we can see a superposition. In that superposition, there is a relative phase factor, which is specified by the bit phi sub minus 1. This bit is coming from up here. It is the label for this initial qubit state of qubit 3. So that's what the Hadamard gate has done. Now let's have a look at what this sequence of 3 controlled unitary gates does. Every time we apply a controlled unitary gate, we're going to add a bit to this sequence in this bit string at the top. So we're going to have phi sub minus 1, and then phi sub minus 2, then phi sub minus 3, and then finally phi sub minus 4. That's as far as we're going to go in the 4-qubit quantum Fourier transform. So what does this bit string actually mean? It is a binary fraction. So this first term is getting multiplied by 2 to the minus 1, and then we have 2 to the minus 2, then 2 to the minus 3, and then 2 to the minus 4. So the subscripts in this notation, they actually match the power of 2 that each of the terms is getting multiplied by. And it's a lot more clear in summation notation. So we have the full 4-bit string over here. So we have 4 bits in a string, and they're actually being used to label the initial computational basis state at the beginning. So before we apply the quantum Fourier transform, we have that initial computational basis state. And it is labeled by those 4 bits. And those same 4 bits are showing up in this binary string that is inside the complex exponential. So where is this phi sub minus 2 term coming from? Well, it's coming from this controlled 2 gate. You can see that the control qubit is changing. First, we have the control circle over here. This symbol is on qubit 2. And then we have qubit 1 and then qubit 0. So the control qubit is changing. And the control qubit determines which one of these bits we're going to add to the string. And the place that we add those bits is determined by this label inside this box. So we have 2, 3, and 4. So that's the second, third, and fourth place in this bit string. And you can see in this format, the subscript matches the power of 2, and it also matches the gates over here. But that's only present in this first sequence, because in these following sequences, we're going to have shifts, and these guys are not exactly going to match. So the target is remaining the same in this sequence. It is just the controls that are changing. Now let's move over to the second sequence. So we apply the Hadamard gate to qubit 2, and then we apply these controlled unitary operations. And the control qubit over here is qubit 1, and then we have qubit 0. But the target in this sequence is always qubit 2. So let's see what happens to the quantum state. So first we have this relative phase factor with phi sub minus 2. That phi sub minus 2 is being sourced from up here. And then we are adding phi sub minus 3 and phi sub minus 4. So those are being sourced from the control qubits. So we have phi sub minus 3 and then phi sub minus 4. Those are the labels of these initial qubit states. And if you follow this vertical line all the way down to the circle, that circle is telling you where the control qubit is. And that's where we're sourcing those bits from. And you can see we have a 2 and then a 3. So we're adding it at the second place. That's this phi sub minus 3. And then in the third place, that's the phi sub minus 4. So now we have a bit string that contains 3 bits. So we're missing that first bit. We've chopped it off. This is the same as multiplying this initial bit string over here on the left by a factor of 2. So we're shifting everything. We're just multiplying by a factor of 2, and that shifts everything. So what is that actually doing over here? It is shifting the phi sub minus 1 term over the point. So we could also write this as phi sub minus 1 point, phi sub minus 2, phi sub minus 3, phi sub minus 4. But if we did that, we would be including this redundant bit over here, which is actually an integer. And that integer is going to multiply 2 pi. So we'll have an integer multiple of 2 pi in a complex exponential, and that's the same as multiplying by 1. So we are free to omit that bit that goes over this point. So we're just interested in the fractional part. So that explains this second sequence. Now let's have a look at the last 2 sequences. So this second last sequence is being applied to qubit 1. Then qubit 1 is associated with this bit, phi sub minus 3. So that phi sub minus 3 bit is occurring in this superposition over here. After we apply the Hadamard, we have phi sub minus 3. And then when we apply this controlled 2 gate, that's going to give us an extra phi sub minus 4. So this is a 2-unit shift. So we're shifting that bit string by 2 units now. And that's why we're missing the first 2 bits. And finally, we're going to have the Hadamard gate applied to qubit 0. And then we have no controlled unitary gates. We don't have any other qubits to act as the control. So we just have this Hadamard, and this Hadamard is introducing this phi sub minus 4 term over here. So now we're shifting 3 units. And pay close attention to the normalization coefficient in each of these snapshots. So when we just apply a single Hadamard, we have 2 to the minus 1/2. And that explains this normalization coefficient in the first sequence of gates. And then in the second sequence of gates, we've applied another Hadamard, and so we have 2 to the minus 2 on 2. So we have a 2 up here. That's because we have 2 of those normalization factors for both of these superpositions. Both of these superpositions give us a factor of 2 to the minus 1/2. And we combine that into one factor. And then when we apply a third Hadamard, that gives us 2 to the minus 3 on 2. So in these two snapshots, we can see the coefficient of 2 to the minus 3 on 2. That's because we have 3 superpositions. And then finally, we have 2 to the minus 4 on 2 after we applied this final Hadamard. So that's because we have 4 superpositions. But the order of this tensor product is incorrect. So we can imagine implicitly there are tensor product symbols in between each of these brackets. So what do we have to do? We have to apply a swap gate, which swaps the first and the last qubit. And then we need another swap gate, which swaps the second and the second last qubit. And that's it. That's going to allow us to swap all 4 of these qubits. So this first superposition gets put to the last place. The second superposition gets put to the second last place. This second last superposition gets put to the second place. And the last superposition gets put to the first place. That is the action of these swap gates. And these X symbols with these horizontal lines, they're denoting swap gates. And for the 4-qubit quantum Fourier transform, we require 2 of these swap gates. So this expression in the bottom is the tensor product definition of the quantum Fourier transform for a 4-qubit system. We have explored diagrams that depict the quantum Fourier transform for a single qubit, for 2 qubits, for 3 qubits, and for 4 qubits. Let's conclude this video by generalizing to mu qubits, where mu is a positive integer greater than 4. Let's first elaborate on the labeling for these qubits. So on the left, we start off with x sub mu minus 1, and then we see mu minus 2 as the subscript. And we keep going all the way to 1 and then 0 as the subscript. So the largest value is on the left, and the smallest value is on the right. Underneath these labels, we can see the initial qubit states. And those initial qubit states are labeled by bits. And here we have phi sub minus 1, phi sub minus 2, all the way to phi sub 1 minus mu, and then phi sub minus mu. So that is a mu bit string that is used to label the mu qubit computational basis state that we are initializing this mu qubit register in at the beginning of the procedure. So that's before we apply the quantum Fourier transform. And then to implement the quantum Fourier transform, we need to apply a sequence of unitary gates. The first sequence that we can see over here is a Hadamard gate followed by controlled unitary gates. And we can see we start off with this label 2, and then we go all the way up to mu minus 1 and then mu. So the target of these controlled unitary gates remains the same in this sequence, but the control qubit changes. The control qubit starts off at this second value of mu minus 2, and it goes all the way down to 1 and then to 0. So that's this first sequence. And then after that, we have the second sequence of gates. We start off with a Hadamard gate, and then we have a sequence of controlled unitary gates. But there is one less controlled unitary gate. So we don't go all the way up to mu, we go to mu minus 1. And then we have all of the intermediate gates. So we have patterns just like this, where we reduce the number of controlled unitary gates after the Hadamard in these sequences. And we keep doing that until we get to the second last sequence. And the second last sequence consists of a Hadamard gate applied to qubit 1, and then we have a controlled unitary gate with this label of 2, and that is it for this sequence. And then the final sequence just has a Hadamard gate by itself. So there is no controlled unitary gates after this one. And you can see that I've split up this diagram into 2 halves. So this left half over here shows the first and the second sequence, and then you can see some dots at the bottom which show that there are intermediate sequences. And then we start after all of those intermediate sequences in this right half, and we get to the second last sequence, and then this last sequence, which just contains a single Hadamard gate. And after we've implemented all those sequences of Hadamards and controlled unitary gates, we have to swap the order of the qubit states. So we can swap the first and the last, and then we can swap the second and the second last, and we keep going until we've swapped all of the qubit states. And that is going to get us to the final state. And that is what happens at the end of the quantum Fourier transform. So we can actually describe this with the tensor product definition of the quantum Fourier transform. So this is a generalization to mu qubits. This is what the quantum circuit diagram looks like. And I've just broken it up into 2 slices, and I've zoomed in so you can see all of the details. And everywhere where you can see dots, that is just showing that we have omitted parts of this diagram. These vertical dots tell us that we have omitted unitary gates, and horizontal dots tell us we have omitted the qubits in the middle of the register. So we're only showing the first, second, second last, and last qubits. So that is it for this video. We have seen many interesting patterns in these diagrams, and hopefully they will help you understand the quantum Fourier transform. The quantum Fourier transform is essential in the process of phase estimation. And phase estimation can be adapted to perform many outstanding quantum algorithms, which includes the order-finding subroutine of Shor's factoring algorithm.